Today will be much ado about nothing, because we'll talk about the vacuum. Okay, and there's a lot to be said about the vacuum. For example, that it's not the minimum energy state. Okay, which is a weird thing. So let's remember, we found that when we use different choices of mode functions, let's say mode functions v as opposed to mode functions v tilde, then these different choices of mode functions allow us to express the quantum field equivalently in different ways. So our quantum field is the chi, which you remember is a rescaled version of the phi, as we're really interested in, but the chi is nice because it doesn't have a friction term in its Hamiltonian or in its equations of motion. So we have that the same, the quantum field can be expressed either using one set of mode functions, vk, or another set of mode functions, v tilde k. If we use the v's, then they come with their own A and A dagger operators, and we can build a Fock basis using those A and A dagger operators, a Fock basis of the Hilbert space, or alternatively we use some other modes, some other set of mode functions. They come with their own A and A dagger operators, let's call them the tilted ones, and using those we can again construct a Fock basis, a Hilbert basis of our Hilbert space, and it's the same Hilbert space, just a different basis. So in particular, when we use one set of mode functions, let's say the v's, and the A daggers, then there is going to be a particular vector in the Hilbert space that is singled out, because it's the vector that's being annihilated by all of the a's. And similarly, if we choose another set of mode functions, well then another vector in the Hilbert space, in the same Hilbert space, will be singled out, namely the vector that's annihilated by all of the A tilde. And so, whenever we choose a mode function, whenever we choose a set of mode functions, we are already implying a vector that's singled out in a Hilbert space, namely the vector that's annihilated by the annihilation operators that come with that set of mode functions. So you see there is a one-to-one correspondence between choosing a set of mode functions and singling out a particular vector in Hilbert space as the one that's annihilated by all those A's. I shouldn't say one-to-one correspondence, actually, because as we will later find out, there are mode functions, choices of mode functions that lead to the same vector that's annihilated by the A. Basically, if the Bogoliubov transformations map A's into A's and A daggers into A daggers without mixing them, then the vacuum state stays the same. So not the vacuum state, the state that's annihilated by the A stays the same. Okay, now I want to link this up with another choice. So far we discussed that two choices are very much linked. The choice of the set of mode functions that we use, and the singling out of a particular vector in the Hilbert space, which is the one that's annihilated by the A operators. Now, very important for today's lecture will be the fact that these mode functions are, in particular, solutions to the Klein-Gordon equation. And the Klein-Gordon equation is a second-order equation, second order in time, which means that if you choose a particular point in time, and at that point in time you give the amplitude of a mode function and its derivative, then the equation of motion, the Klein-Gordon equation, will determine what the mode function is at all times. Right? Second-order differential equation, if you know the initial condition, the amplitude and the derivative, then that determines the thing overall. So let me connect the dots. If you pick a particular time, and at that time you are specifying the amplitude and the derivative of a mode function, then that fixes the mode function for all time. And having chosen a set of mode functions, Having chosen a set of mode functions means also you've chosen the A and A daggers that come with them, and therefore you've chosen a particular vector in the Hilbert space, namely the one that's annihilated by all the A. So let me put it all together again, because it just comes up later in the context of more complicated considerations, so I want to discuss it now in isolation. We said that choosing a set of mode functions implies a particular vector is singled out in the Hilbert space, the one that's annihilated by the A. Now, the choice of mode functions is equivalent to a choice of initial conditions. Right? So if for every k you specify the amplitude and the derivative, then you have implicitly already specified the mode function completely. Therefore, specifying amplitude and derivative at a particular time, for all of the k, already determines which vector you're singling out in the Hilbert space. Okay? We will come back to that a little later. Okay, so what's the dimension of our space of mode functions? Remember, we look at every k, we can look at every k separately because the k's, well, you know, that's why we did the Fourier transform. So for each k, the space of possible mode functions is a two-dimensional complex vector space. And any mode function is a linear combination, therefore, of one mode function and its complex conjugate. So the point is that if V is a mode function, in other words, if V is a complex solution to the Klein-Gordon equation, then V star is a complex solution to the Klein-Gordon equation. The two will be linearly independent and span the two-dimensional space. Therefore, for any other mode function, there must exist alphas and betas such that this linear combination holds. It's just a convenient coincidence that it goes only to the second time derivative, which means that we have only a two-dimensional solution space, which means that the V and the V star generically span that two-dimensional vector space. Okay, so these mode functions can always be written as linear combinations of those mode functions, and vice versa, of course. We can solve that equation by complex conjugation and taking suitable differences. We can also use this to express the V in terms of the V tilde. And this comes up later also as an exercise. Now, we know that the field can be expressed this way or that way, and we know that the V tildes are linear combinations of the V and the V star. Therefore, we can plug that expression for the V tilde and the V tilde star into here. And then from that, by comparing terms, we can determine that, you see, by simply collecting together the coefficients in front of the basis vectors V and V star, we can then determine from that the A and the A dagger operators, the A and A dagger are related to the A tilde and the A tilde dagger through this equation. It's really just a two-line proof. And I hope that you'll find the time to do that once. It's just, you know, the Bogoliubov transformation. It's crucial to all of quantum field theory in curved space and also in condensed matter physics. It comes up all the time. So when you can express a field in two ways like this, you know that because of the finite, in fact, two-dimensional nature of the solution space, you have this relationship between the mode functions, and that translates into this relationship between the creation and annihilation operators. Now, we take this Bogoliubov transformation as the starting point for calculating the unitary transformation that maps the Fock bases that we can generate using the A and A dagger to the Fock bases that we can generate using the tilted ones. And that unitary transformation we calculate by starting with finding out how we map the vacuum of one representation into, I shouldn't say vacuum, how we map the vector that's annihilated by the A operators into a linear combination of vectors in the other Fock bases. So what we found was that by using this equation, we found that the vector that's annihilated by all of the A operators is this linear combination of multiparticle vectors. I mean, I shouldn't say multiparticle really, because we didn't identify what is the vacuum state. But it's definitely a complicated state in the other bases. So this allows us to say that this vector is mapped by the unitary change of basis map. It is mapped into that vector. We can from that easily also determine what the image under that unitary change of basis is when we want to map not that vector, but the vector where there's one of the A daggers acting on it. No problem, because we just have to express that A dagger using that equation in terms of tilde operators, which we then have act here, right? So we act with the A here, the A dagger here, and then that's equal to a certain linear combination of the tildes, and they act on that, and in this way we can map every basis vector in the Fock basis over here into the image vectors in the other Fock bases. So we get the unitary map that maps these basis vectors into those basis vectors there. When would we need that? So here's an example scenario. Let's say we look at one choice of mode functions and another choice of mode functions. And let's assume we chose those two sets of mode functions cleverly, such that the vector that's annihilated by the A operators corresponding to this corresponds to the actual vacuum state, the actual no particle state at the time eta1, and we chose the other set of mode functions in such a way that the vector in the Hilbert space that's annihilated by the tilde A operators happens to be the vacuum state at another time, eta2. Okay? So as we discussed earlier in previous lectures, we are working in the Heisenberg picture, therefore the state of the system does not evolve in time, but the operators evolve in time. For example, the Hamiltonian evolves in time. And what also involves in time is the meaning of Hilbert space vectors. In particular, which state is the no particle state? That state may be described by a different vector at different times during the evolution. So let's assume we know, for some reason, we know which vector in the Hilbert space is the vacuum vector at eta1. And let's assume we know which vector in the Hilbert space is the vacuum state, is the no particle state at time eta2. And then let's assume that the vacuum vector at eta1 is the vector that's annihilated by the A operators coming with this mode function, and the other vacuum is, the later vacuum is the one that's annihilated by the A tilde operators that come with this set of mode functions. Then what this equation here is clearly telling us is that since this state is, by assumption now, the actual no particle state at time eta1, and since this state is the actual no particle state at time eta2, and we have this relationship, we can conclude that particle creation takes place if we start out in the vacuum. Let's say the system is prepared in the vacuum at time eta1, so this is the state of the system at time eta1. Then, because we are in the Heisenberg picture, that's not evolving. So our system is always going to be in that state. But at a later time, this is the vacuum state, and therefore this is not the vacuum state. Instead, it is a multi-particle state. So if we prepare the system in the vacuum, then at a later time, it's going to be in an excited state with lots of particles present. In fact, it looks like infinitely many particles would be present, because we have here in the exponent a power series with arbitrarily high powers of A-dagger operators, so they all act on that, creating particles. So it seems like there's an infinite number of particles being created, and it's something that we'll have to look into, whether it's really infinite. So the first point is that our equation T, the Bogoliubov transformation between the two bases, this transformation tells us that there is a finite probability amplitude for finding an arbitrarily large number of particles. For example, you could take, if you write this out as a power series, there will be a term where this is taken to the 1/1,000,000th power, which means that 2 million particles would be present. There's an overlap between, basically the coefficient in front of that tells you the probability amplitude for finding 2 million particles, having been created out of the vacuum. But that could be a problem if this was our prediction, that we have infinitely many particles, because we would expect that infinitely many particles come with infinitely much energy, and that would mean that as the universe expands, so many particles are being produced that the energetic impact can no longer be negligible. And therefore, that would invalidate our assumption that the quantum field is riding on a space-time that's expanding according to the scale factor A of t or A of eta, no matter what. Remember, our assumption so far has been that the quantum field lives on a background space-time that's expanding anyway. The background space-time is not interested in what the quantum field does. It's just evolving classically. We just have FRW solution, that's it, and the quantum field lives on it. But here we see there's a danger that we might be predicting that the quantum field produces so many particles because of the expansion that the energetic cost is high. But if it produces a large impact onto the energy momentum tensor, well, that through the Einstein equation should feed back into the evolution. So we'll have to check on the number of particles and the amount of energy that's actually involved in this. So let us calculate the expected number of created particles. How do we do that? Well, remember from quantum mechanics that there is a number operator for harmonic oscillators, and we will use that for our mode oscillators. In a quantum harmonic oscillator, this operator is the number operator, because its eigenvalue is the number of the level of the excitation of the harmonic oscillator. Right? So if you apply this operator on a dagger to the power n, which would be a harmonic oscillator in the nth excited state, then, or mode oscillator in the nth excited state would represent n particles present. So this operator acting on that state, if you work it out with the commutation relations, just gives you n times a dagger to the power n. So in other words, this vector is an eigenvector to the number operator with eigenvalue n. If you haven't done that calculation, then please do it. In quantum field theory, we have one harmonic oscillator for every mode. So we have lots of number operators. We have a number operator for each individual mode. And in quantum field theory, that will be related to the number of particles. So let's assume that at some time eta, the state 0 annihilated by, and by that I mean the vector in Hilbert space, which is annihilated by the AK operators. See, without the tilde here, so also the A operators will not have a tilde. So let's assume that at some time eta, this state happens to be the actual vacuum state, and whenever in quantum field theory and curved space we speak of the vacuum state, we mean by that the no particle state. Doesn't mean lowest energy, as we will find out. What we always mean by vacuum state is the no particle state. So let's assume that this is the no particle state at a particular time eta, and that of course comes with a particular choice of mode functions, right? It's the vector that's annihilated by the AK operators, which come with a particular set of mode functions, and our convention is going to be that it's going to be the untilde ones. The V without a tilde, and the 0 without a tilde, and the A, and A dagger without a tilde. So the assumption is at a time eta, that's the vacuum state. And then, as we said earlier, if we look at the same time eta, when it's still true that this is the vacuum state, when we look at the state AK dagger to the power n acting on this, then up to normalization, this is going to be a state with n particles of momentum k. The harmonic oscillator is excited by this much, and we had a hunch that this is the case because we noticed that when you increase the excitation by n, if you increase the excitation by 1, then the energetic expense for that is exactly the energetic expense for a particle that would have the momentum k. Okay, so the interpretation is that if at a particular time this is the vacuum state, then that is the n particle state, where the n particles have momentum k. If you want to describe a state that has more particles of other momenta, you just multiply here the other A daggers for the relevant momenta. Now, assume that at the time eta, the system is neither in its vacuum state, nor is it in an n-particle state, but instead assume that the system is in an arbitrary state omega, which is a linear combination, of course, of the vacuum and the states of definite particle number. Then we can calculate the expected number of particles of momentum k as this expectation value. So the state omega might have all sorts of numbers of particles of various momenta in it. If we want to know what is the expectation value for finding what the expectation number for the number of particles of momentum k, this is the expectation value that we have to calculate. Let's do it for the case that we are considering here. We know that at time eta 1, the system was prepared in the vacuum state, and at time eta 2, it's no longer in the vacuum state. So let's find out how many particles to expect at time eta 2. This is how we calculate that. The state at time eta 2, sandwiching the number operator for particles of momentum k. The number operator for particles of momentum k at time eta 2 is the number operator written in terms of the A tilde operators. Because at the time eta 2, the vacuum state is the state annihilated by A tilde. And therefore the number operator is the operator generated by A tilde dagger A tilde. The state of the system, however, omega, the state of the system is, because we work in the Heisenberg picture, still the state that we originally prepared, which is the state 0, which is without a tilde, which is the state that is annihilated by the A without a tilde. It's the state that at time eta 1 was the vacuum. So this expectation value is the expectation for the number of particles with momentum k at time eta 2, given that the system was in the vacuum state at time eta 1. Okay, so how do we calculate that then? Remember we had a Bogoliubov transformation earlier today, which allowed us to express the A operators in terms of the A tilde operators. Got to be linear combinations of them. Now you can calculate also how, therefore, A tilde can be expressed in terms of the A and the A dagger operators. Just a bit of a linear transformation there. And I'll leave it to you as an exercise to work out exactly how the inverse Bogoliubov coefficients A tilde and B tilde are related to the forward Bogoliubov coefficients alpha and beta. So the alpha tilde and the beta tilde are simply some complicated ratios and products of these alphas and betas. Now once we have the A tildes and the beta tildes, we can go into that expression here and express the A tilde and the A tilde dagger in terms of the A and the A dagger. That's very useful because we don't know how this thing is acting on that a priori, right? Because this is without a tilde, that's with a tilde. But the Bogoliubov transformation allows us to express the A tilde in terms of these. Okay, so we plugged it in here. We get that this A tilde dagger becomes that expression. The A tilde becomes this expression. And when we work that out, we find out that, well, let's just see. We have that this A is annihilating that, okay? We also have that the A dagger is annihilating to the left. So that gets rid of several terms. In particular, this term, because here we have an A annihilating to the right. Here we have an A dagger annihilating to the left. Here we have an A annihilating to the right again. And the only terms that survive in this are terms where there is an A acting to the left and an A dagger acting to the right. And that arises from the product of this term with that term. Okay? Here an A acting to the left and an A dagger acting to the right. So we get the term beta tilde star beta tilde. This is the only term that survives here. We use the canonical commutation relation between the A and A dagger to flip the sequence of the two such that the A is to the right and annihilates on the vacuum state over there. And we just get what the commutator is, which is the identity. And so we are just left with this. This is an important result. What it tells us is that the amount of particle production is given by the modulus squared of the beta coefficient of the Bogoliubov transformation. It also means that if you have a Bogoliubov transformation that doesn't have beta coefficients, where the betas are 0, then you still have a Bogoliubov transformation, but you won't have particle creation. Okay, so just to put it all together, the expectation value of the number operator of particles of momentum k at the late time eta 2 is given by this modulus squared here. So then what about the total particle number? But there we have to sum over all k, and that just gives us the sum over all moduli squared of the beta coefficients. We are assuming here, as you can tell by the fact that we are not integrating but we are summing, we are assuming here that we have an infrared cutoff. For example, that the system is in a box, so that we have a series rather than an integral here. You see, if we didn't put it in a box, if we didn't look at an infrared regulated quantum field theory, then the number of particles created could only come out to be 0 or infinite. Because either there's no particle production, it's 0 in this case, or if there's any particle production, well then because space is infinite in our FRW universe, it will have to come out infinite there. But with a finite volume, we can then calculate what the particle production density is. So we can divide this total number of particles expected to be produced divided by the volume, and that would give us the density of particles that is being produced. And that density stays a finite value even if you then let the volume go to infinity. It turns out that the particle number in this case comes out finite, and of course we also want that the energy carried by those particles would be finite. We will go into more detail on this later on. I just want to raise awareness of the issues at this point. Any questions so far? Because now we move on to a difficult topic where you really need to be completely sure about what we said earlier. Guillaume?
If we had a non-zero coherent state instead of a vacuum, we were applying the Book transformation like that, and should be checking out the number expectation value. Right? A coherent state is always like the modulus of its coherent state parameter. If you apply this transformation, then the alpha would matter. Right? Usually we always say the betas, the alpha doesn't really matter, but like only the beta changes the number expectation value. But if you have a non-zero, why didn't we do the calculation? I'm kind of asking. Like if you have a non-zero, just a coherent state, and then you...
just don't mix up exactly. I mean, the coherent states have properties that are labeled by a complex number, but that's not to be confused with the alpha and the beta. It's just not exactly the same.
I know.
Yeah.
I'm just saying.
But you see the point here, right? In this calculation, no particle production unless the betas are non-zero.
Production, yeah.
But
no I'm saying the alpha parameter in the Book transformation also matters if you have a non-vacuum.
Yeah.
It's going to change your particle.
Mm-hmm.
So you know, even if you have only an alpha there, you might see a difference, let's say, in a coherent state.
Yeah, it's not trivial. I mean, for example, when we looked at the earlier case of the German harmonic oscillator, there was no beta coefficient, right? But it was still non-trivial and you generated coherent state. Okay, so now we come to a crucial question where we think we know how it works sufficiently well so that we can do the inflationary scenario and incorporate it in the standard model of cosmology. But a lot of questions are open in this business that I'm going to talk about now for the generic case, generic curved spacetime, when it's not FRW spacetime with some, a well-behaved FRW spacetime. And the issue that we are addressing now is how to identify which state in the Hilbert space is the vacuum state. So far, we just said, let's assume that at time eta 1, the vacuum state is such and such state annihilated by A operators that come with certain mode functions. But by what argument can we convince ourselves that this might be so? How can we identify which state in the Hilbert space is the no particle state at a particular time? If we can do that, then we can hopefully identify, oh, okay, that's the vector in the Hilbert space that describes no particles. It would be convenient, therefore, to arrange to use those mode functions for which the A operator annihilates that state. And then we can write down immediately multi-particle states and so on. But how do we get this first hint? How do we first identify which vector in the Hilbert space describes no particles at a particular time? So that's the thing we were interested in. What is the state which is the vacuum at time eta? Now, here's the question. Is that state one of the infinitely many states that we can write down in this way? So you choose one set of mode functions, Then it comes with A operators that annihilate some vector in the Hilbert space. Another set of mode function annihilates another operator, and it leads to A operators that annihilate another vector, etc. And so we are hoping that the vacuum state at time eta will be one of those vectors, so that conveniently we can then choose our mode function such that the corresponding A operator annihilates the vector that we identified as the vacuum state. As we will see, we can do this if the vacuum state actually exists. We can do this, and the vacuum state will be unique up to a constant phase, a prefactor. So our aim is going to be to identify which mode function it is, which set of mode functions is it. So to identify the vacuum state at the time eta will be to identify that set of mode functions V whose A operators annihilate that vector. So it will boil down to the question of which is the vacuum state will boil down to the question which mode function, which in turn boils down to the question which initial conditions. Because if you remember, to fix a mode function is simply to fix its initial conditions at some point. So you choose at a particular point in time, one moment, you choose at a particular point in time amplitudes and the first derivative. That means you've chosen the mode function. Once you've chosen the mode functions, you've chosen which A operators, which A Dagger operators, and that determines which vacuum you've chosen. So to identify the vacuum state mathematically corresponds to identifying, to identify the vacuum state at time eta corresponds mathematically to identifying which initial conditions to impose on your mode functions, such that you get mode functions for all time, which come with A operators that annihilate the state in question.
Mohammed. Yeah, I'm just a bit confused. What is the vacuum state? Because in our definition, it said the vacuum state is the state of no particles. Mm-hmm. But then in our interpretation of the quantum field theory, the no particle state is the state annihilated by the mode functions that we choose.
No. I haven't told you at all yet how we would identify which vector in a Hilbert space is the no particle state. So far, I've only said that if by some other argument that I'm aiming at, if by some other argument we know which vector it is, then will be convenient to choose the mode function suitably so that this vector is annihilated by that mode function's A operators. But I haven't really told you an argument yet for how to identify which vector it is.
Okay.
It hasn't come up yet, right? Because remember, we can really express our field with whichever mode function we want. It's just that it's a convenient choice to choose the mode functions whose A operators annihilate the vacuum, at least at some point, right? At another point in time, another vector is the vacuum state, and therefore at another point in time, it might be more convenient to work with another set of mode functions. And then yet another time, another vector in the Hilbert space is the no particle vector, right? And then again, we should really choose another set of mode functions for convenience. We don't have to, but it would be convenient at that later time to work with a set of mode functions whose A operators are annihilating what is the vacuum then.
Okay, I guess the difficulty I have is that we probably don't have enough information about the vacuum state to determine it now.
Yeah, but we're getting at it.
Okay.
I haven't really given you any indication yet what it might be. Okay, so that's the aim though, right? That once we have identified it, then we choose our mode functions such that its A operators annihilate that vacuum state. But how to specify the vacuum state? How shall we do this? Now, here's this equivalences that I was trying to prepare you for. And you will notice that to specify a vacuum state at a particular time eta is equivalent to specifying a suitable set of mode functions, which is equivalent to specifying the initial conditions of the set of mode functions at some choice of time, at your choice of time. This time a priori has nothing to do with the time at which we want to identify the vacuum, right? It's just that we want to nail down a choice of mode functions, and we can do that by choosing at any arbitrary time we want the initial condition and its derivative, amplitude and derivative. That will fix what the mode function is at all times because it's a solution to the time-Gordon equation. In other words, the identification of the vacuum state at eta boils down to specifying for each mode k two numbers, namely the amplitude of the mode function and the derivative of the mode function. So the amplitude we may call r, and the derivative we may call s, at some point of time of our choosing. We may choose to put our initial conditions here at that same time, even though there is no need to do so. But we could choose, for example, that time eta here. So at least mathematically now we have it down pretty easily, right? We just have to specify those two numbers here, two complex numbers, and that will fix our mode function. I mean, for every k, we have to fix those two numbers. That will fix our mode functions, and that will mean that we fix what the A operators are, and the vacuum is the one that's annihilated. Okay, but I've just shifted the problem to identifying the correct numbers R and S. We still don't know how to identify on physical grounds what the vacuum state is. So here's the first attempt. The mathematics cannot tell us the math is good with all possibilities. No, we have to put in some physics now. And the ansatz, the obvious ansatz might be this. Let us try to identify the vacuum state at a time eta as that Hilbert space vector which at that time minimizes the Hamiltonian, lowest energy state. Right? It's plausible, right? No particles, that should be the lowest energy state. It's not going to be true, but let's see how it fails. Okay, so to this end, we will try this. We will choose our initial conditions for the mode functions, R and S, in such a way that when we calculate the expectation value of the energy, it comes out minimal. Okay? Remember that choosing the R's and the S is to choose the vacuum state. And we will choose the R and S such a way that the energy comes out minimal. So we choose the time eta 1, and we calculate the expectation value of the Hamiltonian at that time. The Hamiltonian, if you remember, takes this form here. This is the second time derivative. This is the term with the Laplacian, because we have some I equal 1 to 3, and then here we have the space derivative squared. And then we have the mass term, and then we have the term that came about because of the expansion of the universe. This is just exactly the Hamiltonian of a few lectures ago. Integrated over x, because this is really the Hamiltonian density. Integrate that over x, then we get the total energy there. Now, I leave it to you as an exercise to use the Fourier transform now to turn this into k vectors and so on, so that we don't have derivatives here anymore. And then you get just this harmonic oscillator. And then you plug in the expansion, the mode expansion of the field that we discussed all the time. After the Fourier transform, you can do that. And then you find as a result that the energy expectation value is given by this expression now in the Fourier transform picture. And what we obtain is what we, I mean, just the shape of what we obtain should be quite predictable. See, think of this as Fourier transformed, and then you plug in that. So in particular, you get here the square of phi dot, or phi prime, and here you get k squared times phi dagger, and here you have a phi a chi dagger, right? So you get from here, and from there, because they're square terms, you're going to get roughly this sort of thing squared, with derivatives or prefactors, but this sort of thing squared. So you're going to get a plus a dagger terms squared. So we are going to get a squared terms, a dagger squared terms, and a dagger terms. This is exactly how they come out. Some stuff multiplying a dagger squared, it's really not squared, it's a dagger k, a dagger minus k. And then also some stuff multiplying this. And there's going to be a term with a dagger a and a term with a dagger. Using the commutation relations, we can move this around, and then we have this expression here. Now, because the a dagger to the left annihilates that vector, and to the right, the a annihilates that vector, this term drops out, that term drops out, and this term drops out, and we're just left with this expression here. So the energy expectation value is given by this expression here, where the omega k squared is the frequency of the harmonic oscillator of the mode k, the frequency squared, and it comes out to be k squared plus m squared a squared of eta minus this thing. So in Minkowski space, this would be absent, and the a would be 1, and it would be just the usual omega equal to the square root of k squared plus m squared. But because space-time is expanding, we get this scale factor here, and that non-trivial business over here. And you see that the vacuum expectation value depends on the mode function. Depends on what we choose for the v. And also the expansion shouldn't be too dramatic, because this thing can go negative, and this will change. This can change the sign. We will address that later on. But for now, let's just ask what general structure does that have? Actually, yeah, I can say a little bit more about this. See, if this goes negative, if this thing were dominating, then something very special happens in this. See, this is the square of something real, and that as well. So this is positive, and that is positive. Ordinarily, this is also positive, which means that the energy is bounded from below. What the value of the ground state energy is will depend on the choice of v, the mode function, and we will minimize it in a moment. We will calculate what mode function we should choose such that the energy is the lowest. And then our hope is that this is the vacuum state, the lowest energy state. But notice that because this thing can go negative, because that term may dominate over this term, because this may dominate over that, this may be negative. And when that's negative, the Hamiltonian is no longer bounded from below. Because if this grows big enough, the Hamiltonian, it's bottomless. If you can make this as big as you want, because you can choose the v independently of the v prime. You can choose the v very, very large. And then with this thing negative in front, this could go arbitrarily negative. And so the Hamiltonian wouldn't be bounded from below. That happens when the harmonic oscillator is no longer of this form, but of that form. Then obviously the potential, if the potential goes like this, the Hamiltonian is no longer bounded from below. That's the math of it here. Okay, so what we calculated is, so far, this formula. Let's postpone the discussion of that to a little later. Let's assume it's positive for now. So what we calculated is the expectation value of the energy as a function of which mode function you choose. The expectation value of the energy in that state 0 here dependent on the mode function that you choose, dependent on the v and the v prime that you choose. And then the idea is that we choose the v and v prime in such a way that this energy comes out the lowest, the ground state energy comes out the lowest. And then we say that that vector, at that point, that vector here, will be the one that describes the vacuum state. See, if you change the v, we are changing what that vector is. Right? Because depending on which v we choose, we get different A operators. So they annihilate different ones of these vectors. So we need to minimize this thing. Remember, we defined those coefficients Rk and Sk as the initial conditions of our mode functions at a particular time, and we might as well choose the time in question, the eta 1, where we evaluate the energy. We wouldn't have to, but it will be convenient to choose it this way. So we need to determine the coefficients Rk and Sk. This will determine then a mode function along with its annihilation operator. And this then determines the vector that's annihilated by all of those. And that will be the vacuum state. Concretely, from above, the candidate for the vacuum energy, dependent on the mode functions, is given by this. Again, I just carried it forward unchanged. And using those definitions R and S, we can write this the energy expectation value in this way, as functions of R and S. We want to minimize that expression. We want to choose mode functions in such a way that this energy, the vacuum energy, comes out as small as possible. Now, we cannot choose our v and v prime completely arbitrarily. In principle, as long as we are only looking at the requirement that v is to be a solution to the Klein-Gordon equation, well, yeah, we can choose any arbitrary initial amplitude, any arbitrary initial derivative, and then there's going to be a solution to the Klein-Gordon equation that starts out with this amplitude and starts out with this derivative. But remember that our mode functions are more than just solutions to the Klein-Gordon equation. They also have to obey the Wronskian condition. And the Wronskian condition is this condition, if you remember. You know, the condition that ensures that the commutation relations between the phi and the pi translate into the commutation relations between the A and A dagger. So that is another condition on the R and the S. And what is that condition? Well, it's this. If you just plug in the definitions, that's what it is. So in other words, we want to minimize the energy by varying the R and S, subject to the constraint that this has to be true. Because otherwise you could just say R and S are equal to 0, right? That would pretty much minimize it, but that will forbid it. Can't have R and S equal to 0. So we use extremization with a constraint extremization with a Lagrange multiplier. This is the expression that we want to minimize, and that is the condition that we want to hold. Of course, the condition is really that this is equal to 2i, but because we are going to take derivatives, the term 2i is going to not matter. When we calculate the Euler-Lagrange equations, they always involve differentiation with respect to S and R, and the 2i term is not dependent on S or R. So we might as well drop it in here. Okay, so constraint optimization. We have to differentiate this, to extremize it with respect to our variables. We differentiate with respect to the S star and with respect to the R star. If we differentiate with respect to S and with respect to R, we get the same equations, just complex conjugated. No new information in it. So if we set this derivative equal to 0, we obtain that equation here, just because this thing drops out and that drops out, and we just have this expression here, right? Sk plus lambda or minus lambda r k equal to 0. And then similarly, that Euler-Lagrange equation gives us that condition. And on top of that, we still have the constraint, of course. This one. Now, it's a straightforward thing. I'll leave it to you as an exercise to do. Show that the solution to this problem, solving these two equations and that equation, is that R and S, the RK and the SK, have to be of this exact form, where theta is some real number in the interval from 0 to 2 pi. And we will choose the theta equal to 0 as you can convince yourself easily once you plug everything back in. This overall phase does not matter. So what do we obtain here? We've solved a problem. We've solved the problem of minimum energy. We found that if at time eta 1 we choose that set of mode functions which obeys these conditions, because this is exactly this. These conditions are those conditions, because R was the amplitude, S was the derivative. So what we derived is that if at time eta 1 we impose these initial conditions on the mode functions, then we obtain mode functions at all times such that if we express our quantum field using those mode functions and the corresponding A and A dagger operators, then the vacuum expectation value of the energy, the expectation value of the energy in the state with a 0 left and right, I should say, is going to be minima. And our conjecture is that this state should be identified, being the lowest energy state of the Hamiltonian at time eta 1, should be identified as the no particle state. Okay, so in these initial conditions specify a set of mode functions, which when you plug them into the expression of the field, come with operators A, and that operator A is annihilating a Hilbert space vector 0. And it's not just any Hilbert space vector 0, no, it's that vector which minimizes the energy. Let's see if that works in Minkowski space. In Minkowski space, we have that the scale factor function is simply 1, because it's not shrinking or expanding. And we have that the frequency of each mode oscillator is simply given by k squared plus m squared. Remember that in the expanding spacetime we had a factor of a squared, and then we had this extra term that could go negative. And also the conformal time is then just the ordinary cosmic time. And then we conclude that the vector that we found, this vector 0, is the state of lowest energy at time eta 1, if we choose the mode functions which obey these initial conditions. Now, in the case of Minkowski space, we can easily integrate what that means. We can solve the Klein-Gordon equation with these initial conditions. And the answer is that this is the solution. This is the mode function for all time. If you evaluate that at eta 1, you get this value. You see, if eta is equal to eta 1, this is 0, and you just have that vk of eta 1 is this, right, initial condition. And if you take that solution to the Klein-Gordon equation and you differentiate it with respect to eta, then you get down a factor of omega k, which cancels the square root of omega k and leaves a square root of omega k up here in the numerator. And at eta equal eta 1, this term again drops out. So we just find that v prime is I times square root of omega k, as it should be. So in the case of Minkowski space, this is the mode function that we derived in this way. And indeed, you should recognize that we worked with these mode functions before. That's exactly the mode functions that we worked with before in Minkowski space. So they were actually minimizing the energy. I mean, to be precise, the vector that is annihilated by the corresponding A operators has the lowest energy expectation value. Okay, so now, as an exercise, verify that the state that we here found agrees with the state that we talked about much earlier in the course, that it's really exactly that Minkowski space vacuum. You can also show that if you do this exercise for another time, eta 2, then you get another mode function. You get mode function initial conditions at that time eta 2. You can again solve it, and you get another mode function. And for that mode function, you get the same vacuum state. And that's because they only differ by an overall phase. As you can easily see in this case, only the alphas will differ, but the betas for that Bogoliubov transformation will be 0. It's really a very trivial calculation, but it's instructive to go through it. So what the conclusion then is that in Minkowski space, the same vector 0 minimizes the energy at all times, which is plausible because in Minkowski space everything is time independent. A free field is time independent. So the vacuum at one point in time remains the vacuum at all times in Minkowski space. Now let's come back to our ansatz. We made the assumption that at an arbitrary time eta 1, the vacuum state, the no particle state, can be identified as the lowest energy state at that time eta 1. That was our conjecture here. But that conjecture comes with a prediction. Remember that when the universe expands, the Hamiltonian is time dependent. And the Hamiltonian at time eta 2 is not the same as the Hamiltonian as time eta 1. In particular, the ground state may not be the same, generally won't be the same. Therefore, which state is the vacuum state, according to our definition, will not be the same from time to time, right? Because the Hamiltonian changes, therefore its ground state changes. Therefore, which state is the vacuum state changes if we say the ground state is the vacuum state. But when we have that what is the ground state, when we have that the vacuum state changes from time to time, then we must have particle creation, right? Because the state of the system is frozen because of the Heisenberg picture. So even if we arrange the state to be the vacuum state early on, then later on, the state of the system is still the same, but now it's a different state. That's the Hilbert space. So that's the vacuum state. Therefore, we must have particle creation. In other words, we are here definitely predicting particle creation, and we can calculate how much that is. Now, that's a little tedious to do, but again, I leave it to you as an exercise to actually go through those calculations yourself. Basically, find out what is the actual rate of expansion of the universe today. That's all you need for that calculation. And then you can calculate the current particle production rate that arises just because the universe is expanding. And that current production rate of particles, if we adopt the definition of the vacuum as the lowest energy state, is actually 10 particles per cubic kilometer per year per species. Doesn't feel like much, and it's only 10 particles, right? I mean, if you're talking here about a massless Pangolin field, it would be about 10 particles per cubic kilometer per year per species. But the thing is that experimentally, we have no evidence for particle production of that kind at all. None. And we can compare this rate of production with the particle density that we do observe in the universe today. And what we observe today is that we have in the universe, on average, about 1 billion particles per cubic kilometer. That's just, this is of course the visible matter. Dark matter, we don't know how many particles are in dark matter. But dark matter is like 70%. Visible matter is like 20% of all of the matter that we can account for. And so that just makes a difference of a factor of, even less than 2. So roughly, it's about 1 billion particles per cubic kilometer. And this would predict a production rate of about 10 per year per species. One moment, please. Right? Now, if you give that 10 billion years, then that would be way too much. It would be 10 times more than all the particles that we see. And we don't think that the particles, the galaxies and so on, are there because they've grown by accumulating freshly produced matter. Instead, all the evidence points to the fact that the matter was there from the beginning and it just condensed. So, in other words, this particle production seems to be way too high here.
So, well, we haven't seen the details of this calculation.
Yeah.
Like this, you're assuming that the vacuum state, because you define a vacuum state at a certain time, right?
Mm-hmm.
So you define this at what, the beginning of the universe?
For example?
Why would it be in a vacuum?
No. Here the idea is this. Imagine you look at 2 points in time. One of them is now, and the other is in 5 minutes. Forget about the early universe. Just now and in 5 minutes. Okay, and so for now, you calculate what is the vacuum state now, in the sense of calculating which is the state which is minimizing the energy now. That is a state annihilated by A operators with certain mode functions V. And then 5 minutes later, you again ask, what is the vacuum state now? And again, it's some state that's annihilated by A tilde operators with mode functions V tilde. And there is going to be a Bogoliubov transformation between the V's and the V tildes, the A's and the A tildes, and you can calculate how much particle production it is, and that's what you find.
Okay.
So it's just from now to later. And the only thing you need to know is what the current expansion rate is for that purpose. So it doesn't have memory about what was earlier. It's even the current expansion that's already in contradiction to experiment.
It's just the rate now.
It's just the rate now, but in the past, the rate must have been higher because the universe is, okay, now it might be accelerating again, but the universe was slowing down for several billion years. So the particle production, if anything, should have been higher in the past. That would have been higher in the past.
But are you just adding up like the beta squared norms here, or are you?
Yeah, you basically would have to integrate them, yeah.
But that goes back to my previous comment. You have to consider once you have particles, I don't know, you always need to consider alpha and beta, right? You have to consider.
Oh, I see. So you're saying, what if you already have particles?
Yeah,
and then you want to calculate particle production on top of that?
Yeah.
Yes, you can do that, but it turns out it doesn't really disturb. The presence of particles already, as long as it's few of them, will not impact the production of more particles. Only if you have a lot of them, then they will
you might produce more particles, but you might lose number expectations in stuff that was already there, so then maybe...
Well, that is true. You could always run, when you have the evolution of a system and you have particles being produced out of the vacuum, if you run everything exactly like that, just backwards, you would have that all those particles get sucked up by the vacuum, right? Because the solution works forward the same way as it works backward. So you could have a situation where the universe is shrinking, for example, and there used to be particles, and then those particles just disappear. It's a solution. It's just that would be very fine-tuned and not expected to happen. You're right. In principle, when you have particle creation, you could also have particle annihilation. You would have to calculate through it.
And in terms of gravitational back reaction,
Yeah.
Here we have different observers. They have different notions of time. Let's say, well, we're not quite at the observer.
Yeah.
And then you have different notions of energy for the same state. What is the frame for?
No, we don't have different notions of energy for the same state. There's just one Hamiltonian there, and we vary the state. We vary the state. So we ask which state is minimizing the energy.
Okay, so, and if you have a time-dependent Hamiltonian, then you're not conserving energy. But then that energy should come from somewhere, and since the only thing we're coupling to is gravity, then.
Oh yes. Well, that's right. So when you have particle production out of expansion, then in principle, yes, that energy that goes into the production of the particles is taken away from something, which would be the expansion. So if you had overwhelming particle production, then that should be expected to slow down the expansion. Now, in all of what we do, we're assuming, of course, that the back reaction is small. Later, we will take it into account. But this would require a back reaction. It would be a lot. 10 times more matter than it is now. Wouldn't be a small effect. So let's reconsider now. Is there a better way to identify which vector is the vacuum vector? In the sense that we need a plausible mechanism for identifying what the vacuum state might be, and it better leads to a prediction of less particle production. Right? Because at the moment, if we try to identify the vacuum state as the lowest energy state, as the momentary lowest energy state, then a consequence is a prediction of too much particle production. So therefore, the idea now is to avoid that problem by remembering that the experimental evidence says that we don't see any particles just popping into existence because of the expansion. Let us therefore aim to identify the vacuum state as that state which leads to the least particle production given the expansion that we are exposed to at the moment. For any I mean, not just for today, but just generally. Let us ask which vacuum identification criterion leads to a definition of the vacuum state such that the prediction of particle creation is as small as possible. That will be the adiabatic vacuum definition, or adiabatic vacuum identification criterion. To that end, let us remember that any quantum system does not get excited, or only negligibly, if we change its parameters slowly. So if you take a harmonic oscillator, for example, and you change its frequency slowly enough, then if the harmonic oscillator started out in a fifth excited state, it will remain in the fifth excited state. Or if it starts out in the ground state, it will stay in the ground state. If you vary the parameter of the harmonic oscillator slowly. Now, what is slow? Slow is always compared to something else. So slow means slow compared to the natural oscillation frequency of the harmonic oscillator. And similarly, in the universe, we expect that if the expansion is slow compared to the oscillation rate of the harmonic oscillator, then we would expect that this harmonic oscillator evolves adiabatically, even though its parameters may change, even though its eigenvalues, its eigenvectors may change. The fifth stays the fifth, and the ground state stays the ground state. The system remains in those ground state, in the end state. So generally for oscillators, slow change of their parameters means slow compared to the natural frequency of the harmonic oscillators. So for example, we can take a harmonic oscillator given by a pendulum, and let's say this is the string of the pendulum. Then we can make, this guy is pulling on the string, and can make the string longer or shorter, and that will make the oscillation frequency shorter or, higher or lower. Now, if this fellow is pulling and letting go on that string slowly, with a frequency that's slow compared to the natural frequency of the pendulum, then the pendulum will behave adiabatically. It won't get excited. In fact, this fellow will have to basically hit the resonance to excite this thing. So since the universe, at present at least, expands slowly, we should expect that if we identify the vacuum state correctly, then there would be essentially no particle production. So how can we improve over our ansatz for vacuum identification? For that, let's start with a preliminary consideration. Consider models where the universe is initially Minkowski space, and then it undergoes an expansion. And let's say it undergoes that expansion in an adiabatic way. So it starts out, it's a very peaceful case, Minkowski space, and then slowly the universe starts to expand, and therefore also its omega k of eta for each mode is slowly changing. The omega is changing slowly. We expect, therefore, everything is adiabatic, the harmonic oscillators should stay in the states that they are, and if we identify the vacuum state correctly, we should get a minimum amount of particle production. Now the vacuum state should, in this case, always stay the same vector in Hilbert space. And no particle production means the Hilbert space vector that describes the vacuum stays the same vector. Let us have that sink in, right? So no particle production, in the adiabatic case, no particle production means that the vacuum state is the same vector at all times. Which means that once we figure out what the right criterion is for identifying the vacuum state, it shouldn't matter when we apply it. If we apply it at time eta 1, we get the same identification of the Hilbert space vector, that's the vacuum, as if we did it at time eta 2, assuming that the evolution was adiabatic between eta 1 and eta 2. In other words, if we identify what the vacuum state is at eta 1, then this means we will single out a particular set of mode functions. And if we identify what the vacuum state is at a later time, eta 2, again we identify a set of mode functions. And they've got to be the same. They've got to be the same mode functions. No Bogoliubov transformation between them. It's got to be the same mode functions so that we get the same vacuum state. In other words, when we now find a vacuum identification criterion, which we formulate as a criterion for finding the right mode functions, then that criterion should give us the same mode function whether we apply it here or there, early or late, assuming that the evolution in between was adiabatic. Okay? And that will give us the criterion. There is a unique criterion for identifying the mode functions, namely such that the criterion gives us the same mode function early or late. That's the overall idea. So basically what we will do is we will say, if the evolution is adiabatic, then the mode functions will evolve in a very particular, very smooth way that we can write down explicitly, the adiabatic solution to the equation of motion. And then we will see that this adiabatic solution to the mode function, this adiabatic mode function, has a particular relationship between its phi and its phi prime. And that's what we can use to identify the vacuum. And then once we have that, we can also apply it in situations where between eta 1 and eta 2, the evolution may not be adiabatic. So we will use this criterion to identify which is the vacuum state locally in time, and we can apply that whether or not the evolution between any two such identifications is adiabatic or not. Okay, so in the box we have here, since there is only one vacuum state in the case that the evolution is adiabatic for all times, there exists one set of mode functions Vk, whose vector 0 that's annihilated by the A is the vacuum at all times. So how can we find this mode function Vk? Well, we know Vk at very early times, when the universe was still Minkowski. Remember, this is this super easy case where the universe starts out in Minkowski space, and then it evolves adiabatically. We know that in the very early times, Minkowski times, this is the mode function. Right? We know that because we know how to quantize quantum field theory on Minkowski space. Now, if the evolution is adiabatic, it means that the same mode function, right? The same mode function describes the vacuum state at all times. Which means that all we have to do is take that mode function, and this is the early behavior of the mode function, and we now simply have to evolve it in time according to the Klein-Gordon equation. And that will give us the mode function at all times. Even when it's no longer Minkowski space, as long as it's adiabatic, then that will give us the mode function at all times. And ordinarily this is difficult if you have a generic time evolution of your FRW space time, then you have to go into the Klein-Gordon equation and solve it if need be numerically. But if the evolution is adiabatic, it turns out that you can write down the solution pretty much right away. Namely, if the evolution is adiabatic, you can apply the adiabatic approximation to solving the Klein-Gordon equation. And it turns out that the Vk of eta is then given by 1 over square root of omega k, and here the integral over that phase. Strictly speaking, this is not a solution to the Klein-Gordon equation. But it is a very good approximation to it if the evolution is adiabatic. Concretely, you see, I mean, this was the Minkowski space solution, right? And I'm claiming that when the evolution is adiabatic, then out of the Minkowski space solution becomes the general solution simply by making the omega time dependent, allowing its time dependence, and simply by not just multiplying with the time difference, but integrating over time. In reality, the solution is much more complicated than that, because prefactor and phase will mix generally, but not if it's adiabatic. Concretely, this is a very good approximation. It's the adiabatic approximation if the evolution is adiabatic, and that means that the change of the parameters is slow compared to the natural oscillation frequency of the harmonic oscillator. And concretely, this means if omega prime, the change of the oscillation frequency of a harmonic oscillator because of the expansion, is small compared to the oscillation frequency. Now, you see, omega prime has units of 1 over time squared. So you actually have to divide it by the frequency squared in order to get something unitless. Of course, only quantities that don't have units can be said to be small or large. So if this ratio is small, and if that ratio is small, and this says that the acceleration of the change of the frequency of our modes is small compared to the natural frequency of the mode oscillators, if these two conditions are true, the adiabaticity conditions, if they are true, then this is a solution to the Klein-Gordon equation for all times. All you have to do to prove this, it's an exercise for you, is to plug that ansatz into the Klein-Gordon equation. And you will find it doesn't obey the Klein-Gordon equation. But it doesn't obey it because there are some offending terms which are proportional to this and to that. So if this is small, those offending terms go away, and we really have that this is a solution to the Klein-Gordon equation. Okay, so if the evolution is adiabatic, therefore we don't expect particle creation, then this is how the mode function behaves. And remember that when there's no particle creation, the mode function is going to be the same. The mode functions that generate the vacuum by annihilating it with its A is the same at all time, right, for adiabatic evolution. And this is the mode function that does it. Now, it's actually not necessary that we have the initial Minkowski period. It was just so, conceptually to make it a bit easier, perhaps. So now we try to identify the VK whose vector 0 that's annihilated without, we want to relate to this without talking about an earlier Minkowski period. And the reason is that the universe didn't start out in Minkowski space. We need to free ourselves from that assumption. So the idea is, instead of doing what we did just now, which is to say, let's say the universe starts out in Minkowski space, and then we allow it to evolve adiabatically using the Klein-Gordon equation, we'd like to identify the adiabatic solution even when there was no prior Minkowski space behavior. And we can do that by checking whether this solution, the adiabatic solution, has a particular property that singles it out. And it turns out that indeed the adiabatic solution has a property that singles it out, and therefore we don't need to refer to an early Minkowski period. And what is that property? Well, we notice that the adiabatic solution, and only the adiabatic solution, has the property that if you calculate that at all times it obeys the condition that if you evaluate the amplitude, you obtain a term like this, namely it's a prefactor 1 over square root of omega times a phase. Let me just verify that this is true. Here we go. The adiabatic solution is always 1 over square root of omega times a phase. Okay? At all times, the adiabatic solution has the property of being 1 over square root of omega times a phase. And we have that the first derivative of the mode function is given by this particular expression times 1 over the square root of omega times a phase. And that you obtain by just differentiating it. If you differentiate this mode function with respect to eta, then you get all those terms. Again, I'll leave it to you to verify it. Easy calculation. But the point is that the adiabatic mode function has this form for its amplitude and that form for its derivative. Remember how we earlier identified the vacuum as the minimum energy state. We said that the minimum energy state, and we calculated the R and S coefficients. We calculated the phi and the phi prime, that we're singling out the minimum energy state, saying that if we have the phi and phi, chi and chi prime, or V and Y prime, that's V and V prime, that's the thing. Once we had V and V prime, then the Klein-Gordon equation was giving us the mode function at any time. So now here we have again a criterion for identifying the R and the S, for identifying the V and the V prime. So this is a local criterion, local in time, for identifying the mode function that corresponds to the adiabatic vacuum. What that means is that now if at some time in the universe you want to know which is the adiabatic vacuum, all you have to do is calculate that mode function which obeys this initial condition at that time, this amplitude, and that derivative. And then you can extend that using the Klein-Gordon equation forward and backward in time, even into the future where it may not be adiabatic, even into the past where the evolution may not be adiabatic. But locally in time, you've now identified which mode function corresponds to the vacuum, in the sense that if you take that mode function, it comes with A operators which annihilate the state which at that time are the lowest energy state. So here's the general adiabatic vacuum identification. Consider an arbitrary time eta 1. Assume that the evolution of the mode is adiabatically slow, at least around the time eta 1. Not at all times, but at least the time eta 1 we want it to be slow. We want it to be adiabatic. Then we can identify that state as the vacuum state, as the no particle state, at the time eta 1, whose mode functions are specified by this condition here. This for the amplitude, and that for the derivative. You see, the overall phase constant doesn't really matter. What really matters is that the amplitude is given by this, and the derivative is given by that, all of which you can evaluate because you have the omega k. If you choose that, then if you choose this vacuum identification criterion, then whenever the evolution is adiabatic, you will have minimized particle production at that point. But you can apply it also at times before and after which non-adiabaticity kicks in, right? Okay, so these are, this is to be compared, this condition for identifying the R and the S, for identifying the V and the V prime, is to be compared with this condition. These were the two conditions when we identified the vacuum as the lowest energy state. Then this was the amplitude, and that was the first time derivative condition. So the adiabatic vacuum identification criterion is almost the same as the one where we would say that the vacuum is the lowest energy state, but it's not the same. The difference is this term here. Right? Other than that, this is the same as that, this is the same as that. But the adiabatic vacuum identification criterion would say, no, you have to put that extra term in here. And of course, if the universe is not expanding, if omega prime is equal to 0, that term drops out. Okay, so, well, we can also view this in the Schrödinger picture, but I suppose that just takes a little bit of quiet contemplation, and we are out of time today. I hope that wasn't too much of an overdose, but we had to do it. And you can tell how this is not entirely satisfactory, right? But it's the best we have at the moment for trying to identify what the vacuum state is. And the amazing implication is that really, apparently, the lowest energy state is not the state of no particles, right? So, in other words, the lowest energy state is a state with particles. Not many, but yes. When I taught this a few years back, I raised that issue. I raised the possibility that this may have to do with vacuum energy. Basically, because what it says is that there's a difference in energy between the no particle state and the lowest energy state. So the vacuum state is a little bit elevated in energy. And so I raised that possibility that, you know, somebody should calculate that difference and compare that with the amount of vacuum energy that we seem to now have, which is small but noticeable. I mean, small compared to what quantum field theory would ordinarily predict without renormalization. But it's, of course, more vacuum energy than actually we have in the form of energy from particles. And so one of the students, Siavash Hasanbegi, went and started calculating that. until he found that somebody had that idea before. So we never published it. Now, I think that in that prior work, somebody had that general idea, but we also think that they didn't really carry it out correctly. So I think it's still sort of an open problem. It's just that some wind was taken out of the sails because the idea was there already. It's just that I don't think the calculation has been properly done. But it would be nice to see how much energy it really is. I mean, our impression had been that it was about the right order of magnitude, that difference in energy. So it might just be that vacuum energy in general seems not to gravitate. There's just too much of it. If it all was gravitating, then that would not be consistent with observations. But it could be that this little bit of difference between the adiabatic vacuum and the lowest energy vacuum, that might just be gravitating. We don't know. And I haven't done the calculation myself. I think it's still an open question. Yeah?
So the expansion of the universe is accelerating, or we're pretty sure it is. So should the adiabaticity condition break down eventually?
Eventually, yes. Yeah. Well, in fact, not just eventually, but already. It depends on which mode you're looking at. If the mode has a wavelength that's larger than the size of the horizon, then it's already non-adiabatic. The harmonic oscillator, it's way worse than non-adiabatic because the harmonic oscillator is going to be like this. And if it's true that the universe is accelerating now, then it's true that we do have a horizon. And sure, it would be very, very large because the acceleration is very, very small. But in principle, you could consider wavelengths that are longer than even that large horizon. And for them, it's already non-adiabatic. And for them, we don't know what the vacuum energy of that thing would be. And remember, too, that for them, the harmonic oscillator is not even bounded from below. But you also have to keep in mind that that doesn't mean that we have a runaway solution, because we are dealing here with the chi field, not the phi field. The chi field has a harmonic oscillator like this, or like that. And if the wavelength is larger than the horizon, the harmonic oscillator is like this. And therefore, it's this runaway solution. Doesn't mean, though, that the physical field phi runs away. The physical field has this friction term in it. And the outcome of the evolution for the physical field phi is not going to be that it runs away in its amplitude, but instead that it freezes. Freezes in its amplitude. So, yeah, it's a complicated question. Guillaume?
So, a notion of particle at a certain frequency, you can make sense of it by calculating a detector that's, has a similar kind of gap of energy compared to that frequency. But if you have something that's of wavelength bigger than the observable universe, how are you going to couple to that? How are you going to, like, if there were particles in these modes that are super long wavelength, how would we perceive those?
Oh, that's right. If you have a local detector, then it's hard to see how it would couple two wavelengths that are much larger than itself it is. It's not impossible. I mean, for example, if you take a hydrogen atom, it can absorb photons of a wavelength that are way larger than the size of the hydrogen atom. For example, you could have some fine structure splitting, which is really in the megahertz range or something like that. And the wavelengths of several megahertz is like tens of meters. And still the hydrogen atom can absorb and emit it.
Over a time scale.
Yeah.
That's appropriate.
Right. But in this case, I don't think we need to worry much about the particle picture of it. I think it's more important to see what the contribution to the energy of it would be.
So
and it has been suggested
gravitationally would affect it. Right?
Yeah, and in fact, it has been suggested that the cosmological constant is sort of the zero mode of a quantum field. Because the zero momentum mode of a quantum field is a constant in space.
Right.
So it could be that it feeds directly into the cosmological constant.
So I'm a bit unhappy about this issue of not knowing how to define vacuum properly, because we defined it first, we saw that there are a lot of particles created. And then we say, okay, our condition is going to be, we're going to minimize the particles that are created. But it seems to me that you're missing a lot of criteria in the middle. So I'm wondering about the testability of this. Like, do you have any intuition if any of our criterion that we decide to choose can be testable?
Suppose, yes, you're right, there could be many other criteria. You could add any number of other terms. You know, what needs to be compared is this vacuum identification criterion compared to that one, and of course you could add other terms there. I suppose in order to be convincing, it would have to be both consistent with experiment, which is not much of a problem, but it would also have to be canonical in some way. And it's hard to see what other canonical criterion you could put there.
What do you mean canonical?
Well, this criterion says the vacuum is the state of lowest energy. That criterion says the vacuum is the state of lowest particle production. And any other criterion should be as easy to describe in sort of intrinsic terms.
But it seems to me you can fine-tune your criterion to say, okay, my criterion is if the number of particles created matches the vacuum energy we measure now.
Yes, you could do that. I suppose you could do that. Yeah, so you're saying you choose a state, you choose to identify the vacuum in such a way that the gap between the lowest energy state and the so-defined vacuum state is exactly the amount of vacuum energy that we seem to have. In principle, you can do that, but it probably won't be unique. There are probably many ways to do that. But yes, it would be consistent with experiment, but you wouldn't have a nice physical criterion, intrinsic criterion, right? Rather than just matching experimental data, it would be better to have an intrinsic criterion, such as minimizing energy, minimizing particle production. But also, maybe we should not be too hung up on finding the vacuum state, because how do we know there is one? Consider that, you know, as Guillaume was alluding to it, really we want to identify a particle with a click in a detector. That's solid. And we know that detectors have to be switched on, and they have to be switched off, and they have to have a finite size. And because of that, detectors always have a chance of clicking. Basically, if you have a detector on at a finite amount of time, then by the energy time uncertainty principle, or by the calculation that we did in lecture 8, you find that it has a finite probability of clicking. So as long as you define the existence or absence of particles as the clicking or non-clicking of detectors, then you can't localize particles in time completely, because detectors would have to be switched on and off for the purpose, which gives them a clicking probability and excitation probability just because of the switching, independently of what the environment does, independently of whether or not particles are streaming in. And so to hope that we can perfectly localize and say, you know, there's no particles anywhere, I mean, what does that even mean? What does it mean that at the moment there are no particles? What kind of measurement would test that? I think we are used to thinking in terms of modes and the excitations because it makes sense in Minkowski space, and especially when you're working with particle accelerators and you have to smash into each other, you work with the S matrix of momentum eigenstates, then that's what you do. You calculate how mode oscillators excite each other, and then you can one-to-one translate that into ingoing and outgoing particles in accelerators. But in generic curved spacetime, there is no reason to believe that this carries further.
If if gravity behaved like, you know, it had a certain Hilbert space, then it could click, you know, change its state of gravity. So we would expect that, you know, our notion of particle that we get from an Erdogan detector is transferred over to quantized gravity. Here it's just that we work with like this absolute kind of definition of energy, and then, oh, gravity will see any sort of energy. Well, like physically, ultimately, it's gotta, if it's quantized, then it's gotta
yes,
click, right?
yes, and that, yeah, we will study that. We will have to work on the back reaction, and we will have to consider that gravity itself is fluctuating and how that's interacting with a field that lives under space-time. Yeah, we'll do that. Not full gravity, but you know, perturbations to space-time. Yeah.
So for the initial definition we had for the vacuum state, which was the state which minimizes the expectation value of the energy. So at the end, the problem that we mentioned about it is that it doesn't match experiments by
It predicts too much particle production, yeah.
like 1 order of magnitude.
Well, it says that if the universe started empty, after the Big Bang it was empty, and all particle production was due to expansion, then we would have 10 times more than we actually see, right? But in practice, we have plenty of evidence that shows that the universe didn't start out empty. For one thing, we see old galaxies, even those that are just 400 million years old, right? And so we have an idea of what the matter density then was. And we can see how it diluted over time. And all of that is consistent with the idea that the matter that we see now was there pretty much at the beginning. We don't have to invoke particle production to account for the amount of matter that we have now. So it's really way off. It's not just 10 times more, it's just, you know, we have no evidence whatsoever that any matter was created by the expansion itself, let's say after the CMB was formed. There's no evidence that more matter was created after that.
And this problem doesn't show up in this other definition?
No, because there's basically no particle production. Because we are extremely close to being adiabatic.
But how do we know if we are close to being adiabatic?
When the acceleration is very small. Compared to the oscillation frequencies of the modes. You see, the modes are oscillating pretty quickly, and the acceleration is very, very small. You know, we just about noticed that we're accelerating, looking back over billions of years.
Okay.
Basically, what you have to compare is the wavelength of the modes that we are considering to the size of the horizon. Now, with the presently noticed acceleration, our horizon, because of the acceleration, is, I don't know, in any case, way larger than our particle horizon. It's way larger than 13.8 billion light years. It's way larger than that. So all modes that are of a wavelength shorter than the observable universe, all those modes are basically adiabatic. And nowhere near being the oscillator inverted. During inflation, a very different picture, because during inflation, as we will later discuss, the acceleration was so dramatic that the horizon was only about 5 orders of magnitude larger than the Planck length, which meant that even the smallest of wavelengths were, I mean, not the very smallest, but even very small wavelengths were larger than the horizon length, therefore frozen in amplitude, and we got this amplification of quantum fluctuations.
Okay.
Yeah, we'll do all of these things in much more detail. Yeah. Okay? All right. Have a nice weekend, everybody.